Okay, so what does it mean to find area between curves? It's actually, you can kind of see through the examples what it means. Imagine you had a secant squared curve and a sine squared curve inverted there. You would be interested in finding that blue area, see? Or maybe between these two, this looks like kind of like a Batman logo or something. Here's a cool problem. It'd be nice to find that area. I've always wondered what it is. That's a cool looking shape. I wonder what its area is. I have no idea what that would look like until I draw it, but it might be interesting. I'd like to know the area. Ooh, they took away my pictures. What would I do? Okay, so the concept on this is very simple. Okay, you're trying to find the area between these two curves. So let me just show you how you could approximate it first. So you could technically just imagine trying to break this up into strips. Like this. So this might be your first strip here. And you know this would probably be like a rectangular approximation if you're going to break it into strips. You can use like an LRAM or an MRAM or an RRAM. But looking at that strip alone, don't draw too big, you'll need the space for calculations. What is the area of that strip alone? Well, it's got a certain amount of width, right, delta x. And it's got a certain amount of height. How would you find the distance from here down to here? Well, it's kind of like if somebody gave you this little picture back in Algebra 1 days, and they say, what's the distance between point A and point B if one of them is right on top of the other, and let's say this is at -1 and this is at 6. What is this distance from A to B?
7.
It's 7, and what's the fastest way to get 7, which is the distance here? What's the fastest way to get the number 7? Delta y. In other words, you do what? Delta means difference. Subtract. 6 minus -1 will give you that length right away, right? Okay, so this distance is, of course, delta y. It's defined as y2 minus y1, you know? And so what I'm going to write here is, instead of writing delta y, I'm going to write 1/2 sec squared t minus -4 sine squared t. Those are the y's anyway. So 1/2 sec squared t minus -4 sine squared t. That is this length. See? So what is the area then of that strip? Length times width, right? So the area of this strip is length times width. And by the way, this is a t-axis. I actually just caught that. So technically this is a delta t, not a delta x. Sorry about that. But my point is, if you're going to find the area of that strip, then you're certainly going to need length times width, right? And this is not the only strip. There's plenty of those strips, right? But they all have that same feature. The top of all of them is at 1/2 sec squared t. The bottom of all of the strips is at -4 sine squared t. The height is still 1/2 sec squared t plus 4 sine squared t. The width is still delta t, see? So if I wanted to combine all of these and smash them all together and form one solid area, that's what integration is for. It's like the infinite sum. So I'm going to pack them all in. I'm going to put this in integral form. And basically, I have this. The delta t becomes a dt, which is the infinitely small version of delta t. You could think of it that way. So the delta becomes a differential. Your limits of integration, of course, are from the leftmost rectangle all the way out to the right. So we're going to be going from -π/3 out to π/3. So those just show up as limits of integration. And this will solve it. Now, if you type this in your calculator, you'll get the answer. But you'll notice in the back of the book, the answer is exact. 4/3 pi. So that means it should have been done by hand. Okay? So let's see if we could tackle this integral by hand. All right? I'll show you. It's not really that bad. So first thing we're going to do is try to figure out the antiderivative of sec squared, but we've seen that before. So what is the antiderivative of sec squared? Simply tan, right? So this is just 1/2 tan t. Okay, that was pretty easy. Plus, oh, we hit an integral we've never done before. What is the integral of sine squared t? Okay, so you could actually use free lunch on this. You could write it as sine t sine t. That sounds cool, doesn't it? Sine t sine t. You could write it as sine t sine t. And you could use parts twice and it would feel like free lunch. Okay? It would feel a lot like free lunch. Or there is an old identity from back in the day that is going to bail us out. And if you remember, there was a rule that said cosine of 2x is equal to 1 minus 2 sine squared of x. It's just an old identity from your pre-calc days. How could we use that little trick here in this context? Isolate sine squared x. Okay, so if I isolate sine squared x, it would look like this. 1/2 minus 1/2 cos 2x. You know what scared me about this integral was the fact that it was sine squared. But if I rewrite sine squared like this, I'm not scared of it anymore. Okay? So here's what I basically did. I'll go back here. I just changed this out for 1/2 minus 1/2 cos 2t. I'm not scared of integrating that. Okay, so I might need one more step of work here. To get that integral figured out. But I don't need free lunch or any of that stuff. Okay, so there's going to be a 4 here. Okay, what's the antiderivative of 1/2? I'm doing this part right now. What's the antiderivative? Half x, in this case half t, right? Okay, so 1/2 t minus, what's the antiderivative of 1/2 cos 2t? Times a half, right? So 1/4 sine 2t. The derivative of that really is negative 1/2 cos 2t. And we're going from negative pi over 3 to positive pi over 3. So actually that identity took away the scary part of the problem for me. I was worried about integrating that quadratic trig, but the identity reduced it to a linear. So, you know what I'm really scared of now is plugging in pi over 3. You know I'm bad at that. I think I can cheat on this problem. Look back at the picture. You'll notice that there's a line of symmetry in this picture. Look closely at the picture. Isn't it true that the left and right side of this are exactly the same? Okay. So isn't it conceivable that I could just find the area of the right side and then just simply double it? I could do that, right? Okay, that's what I plan to do. And it's more than just a convenience. It's a huge time saver. It really is. I'm going to actually use the symmetry to my advantage. I'm going to put a big fat 2 out front. And it is a big 2. What's going to happen is instead of plugging in negative pi over 3 and positive pi over 3, I'm just going to use 0 to pi over 3. So 0 to pi over 3. I'm cheating. I'm only doing half of the area, but I've got a 2 out front to fix it. So this makes it easier for me. I can plug in pi over 3 and 0, which I prefer. See how we can use symmetry to our advantage there? Okay, so plugging in pi over 3, I get 1/2 root 3 plus 2 pi over 3 minus sine of 2 pi over 3. Wait, that's just root 3 over 2. And I can plug in the 0 if I want to, but look, it's going to give me 1/2 tan 0 plus 2 times 0 minus sine of 2 times 0. It's all going to be 0 anyway. So I've got it down to this now. And you'll notice that 1/2 root 3 is the same thing as root 3 over 2, so these cancel out. And the answer is 4 pi over 3. Now let's say that you were really lazy and you decided you were going to do this problem on a calculator instead, and you just ran the whole integral, you didn't do any antiderivatives, and you did your Math 9 button, and you got 4.18879. How could you recover the exact answer? So your calculator says 4.18879. The back of the book says 4 pi over 3. How can you take your answer and sort of fake it and get it back to this? Do you know how to do that? How many pi's is that? 4/3 of a pi. How do you show that? How do you work backwards? Suppose you're going to see this.
Equals x pi.
How would you get the 4/3 out of this? Okay, divide this by pi on the calculator screen, and it will say 1.33333. And you'll say, oh, that's 4/3, and you can reconstruct the exact answer. Okay? It's not a great thing to be teaching you, but remember on the homework, you kind of get to decide if you want to use your calculator or not a lot of times. On the real test, they'll tell you, like, yes, calculator, no calculator. So anyway, if you did a whole problem and you really got stuck on the integral, I don't think you should, like, stop. I think you should pull your calculator and finish it, right? And then try to reconstruct that answer. And then we can talk in the Q&A time about what you did wrong in your work, right? So we're going to finish on the calculator to get stuck in the integral phase. Am I trying to teach you integrals right now? No, what's the purpose of this lesson?
To show how they're used.
To show how they're used, right. The whole chapter is that way, in fact. And what we're really trying to do is find the area between these curves, which is sort of a new idea. Okay, let's look at the second problem. Oh, and one more thing. Even if you do get to use your calculator, this is really important. Hugh knows this. Even if you are allowed to use your calculator, you still have to write this integral. You have to write every detail of it before you bust out and use the calculus. So this would be graded, what you write, and then of course the final answer, even if it's a calculator problem for your response. So let's go to this one. How would you apply that same logic here? Probably want to draw a sample rectangle. Right? The highest point on here is x squared. The lowest point on here is negative 2x to the fourth. See? So how wide is this rectangle? Delta x. How tall is the rectangle? X squared minus negative 2x to the fourth. It's just the high value minus the low value. In other words, the area function will be an integral x squared plus 2x to the fourth dx. The delta x turned into a dx. Where am I integrating from and to? So here are your rectangles stacked up. Yes, they start over here at not negative 2, from negative 1 to positive 1. So those become your limits of integration. Look how easy this integral is. What same thing? Yes, the left and right side of this graph are exactly the same size. So I could get away with changing, use sort of the even function logic, and I could say, let's make this 0 and make this 1. It's less work for me later. And then I just have to remember to put a 2 here. It's twice the area. Good. The antiderivative of this is really easy. It's just 1/3 x cubed plus 2/5 x to the fifth. You're plugging in 0 and 1. So you basically get 11/15, and you're multiplying by 2, so it's 22/15. And that's the area between the curves. So what is my formula? If you need formulas, right? Maybe we should write down a formula for today. All right, so I'm going to go back to the top of the page, and I'm going to write down a formula that you can sort of hang your hat on. Okay? Here's what we're trying to say after all is said and done. That if you want to integrate between two curves, we'll call this one u of x because it's the upper curve, and we'll call this one L of x because it's the lower curve. And let's just assume that this is at x equals a and b. You can find this area in here by integrating from a to b, upper curve minus lower curve, dx. So u means upper curve, L means lower curve. That's not complicated. So there's a little formula. Now, is that going to help us on problem number 3? Look at your problem number 3.
No, because it's left and right.
Something fishy about this problem. What do you notice? Here's number 3 for you. That's this one. What's different about this problem compared to the others? I see a couple differences. Definitely sideways, right? In fact, if you want to, you can change all the y's to x's and all the x's to y's and just use the formula you had up above. Imagine flipping this thing, like turning your head. This is upper and this is lower. You can just make this y equals 2x squared minus 2x and make this y equals 12x squared minus 12x cubed. You can do that and then just pretend that this problem is the same as the other one. Okay? Another option is we could just draw our sample rectangle sideways. Okay? So I'll do that. I'll show you. It's just going to lead us to a slightly different version of the formula. So this would be what the sample rectangle looks like. It goes this way now. And it has a height delta y. And just how wide is this thing? Well, let me give you the coordinates of the endpoints, okay? This endpoint is at 2y squared minus 2y, comma x. I'm sorry, comma y. When y is simply y, x obeys this rule. Kind of weird. And this point on the right is the point 12y squared minus 12y cubed, comma y. 12y squared minus 12y cubed, comma y. So let's look at that rectangle. I want the area of that thing. Its thickness is delta y now. And its length is the rightmost curve minus the leftmost curve. It's kind of like if somebody asked you how far apart are these points. It's 7. You subtract the x's, right? From A to B is 7 units. I'm subtracting the x's here to get the length of that rectangle. So this length is 12y squared minus 12y cubed minus 2y squared minus 2y. That's how long it is this way. Okay. So here is the area of that little rectangle. It's delta y this time times the change in x. 12y squared minus 12y cubed minus 2y squared minus 2y. And therefore your integral is the infinite case of that. You're integrating 12y squared minus 12y cubed minus 2y squared plus 2y. Delta y becomes a dy. And it's very important that your limits of integration are now y values. That is super important. There's 2 reasons for that. One, your differential is y. So your limits must, your upper and lower boundaries must match the integral's differential. It has to. And the other reason is our rectangles are now stacked up this way. See? Your rectangles look like this. Stacked one on top of the other. And the bottom one is at what y value? The very first rectangle down here is at 0. And the one, if you sketch them all in, where's the highest one? 1. At 1, right. So the limits of integration are 0 and 1. You don't want to use any x's for your limits of integration if you're doing a dy integral, see? So we're going to go from 0 to 1. And this, too, is not a difficult integral at all. The antiderivative is very simple, and you're plugging in 1 and 0. What could be easier than that? Okay, so let's just run through it real quick. The antiderivative here is going to be 4y cubed minus 3y to the 4th minus 2/3 y cubed plus y squared, and you're just plugging in 1 basically. That 0 is not even going to count. Plugging in 1 gives you 4 minus 3 minus 2/3 plus 1. Also known as 2 minus 2/3, 4/3. It's kind of hard to believe that this area is 4/3. You know? It's so beautiful. Everything's so clean. Like, just a nice rational answer like that. That's so cool. But that's 4/3, and let's do a little takeaway formula for that too. So what do you do if you have two functions where one is sort of on the right and one is sort of on the left? If your picture looks like this, yeah, we can call this the rightmost function, and we can call this one the leftmost function. They're going to have y's as variables. And you'll be integrating between two y values. We'll call them c and d. So to get this area in here, you would do the integral between c and d of r of y minus L of y dy. If this second version is frustrating to you and it's confusing you, literally go through that last problem and just make all the x's y's and all the y's x's, and it feels just like number 1. The whole thing just inverts. But it doesn't change the area. It just sort of makes you look at it from a fresh perspective. Okay, using this and this, you can handle any problem unless the functions switch. So I'm not going to do this problem today. We're going to do it tomorrow. But look at this problem here. What's going to happen is there's parts where the line is above the curve and parts of the line is below the curve. So we're going to have to change our mind about who's the upper function. So there's going to be parts where we have to integrate one function minus the other, and then it's going to get reversed as the curves pass through each other. The formulas of the day, right? Okay, so we got formulas. Now we can just use them. We'll do some more examples tomorrow. Also, bring your book tomorrow, because you might have some class time to work. Thanks for your patience. A long lesson.
There's nothing due Thursday, right? It's the worksheets.